Okay, thank you very much for the introduction, Prem. Okay, I see a recording started. Oh, there we go. Okay, so first, before I start, I want to say thank you to Kalyan and Prem and the rest of the organization team for inviting me back for my fourth appearance at this series of conferences. Like Michelle was saying yesterday, I think I've been to all of them now, and it's been a great pleasure to be here. This is one of my favorite conferences to attend. I've been a class group person since my earliest days as an academic. They've been a part of my research program ever since I was a student. And it's just awesome to be able to come to a class group where every talk, is touching on class groups or something close to that in some way. It's a real pleasure to be here. And I want to congratulate you guys for, having the vision to put this together. And having the fortitude to keep doing it year after year. I've done my share of conference organization. I know how much work it is. So thanks for continuing to put this on. So my talk is, well, I should say, class groups appear in lots and lots of different areas in mathematics. Already yesterday, we see them popping up in a whole bunch of different places. What I'm going to talk about today, though, is, as Prem alluded to, very computational algorithmic topic of how to do the group operation in the class group as fast as possible. There certainly isn't the most glamorous or sexy sort of a research topic at all. But I mean, if you want to do serious computations involving class groups, it's a really, really important one. I'm trained as a computer scientist. We know that if you want to speed up a computation, you look at the part that the majority of the time is taken in the computation, and more often than not is this basic group operation. So if you want your stuff to run really fast, it's important to be able to do this as fast as possible. So my goal today is just to do a survey of the state of the art of this in quadratic number fields, and also their function field cousins, the hyperelliptic curves or quadratic function fields. Show you what we can do, and hopefully show you a couple of new things along the way in the process. Now, first of all, though, before we begin, this is not an ordinary class group conference. So this is also a celebration of Michelle Waldschmidt's 75th birthday. I have to confess, it's hard to find memes, that combine happy birthday and mathematics in a reasonable and interesting way. This was the best I could find, Michelle. So, hopefully you have a great birthday. Happy birthday. All right. So into the talk then. So I'm going to start just setting the notation and reminding people of the basic objects we're interested in. Give a little bit of motivation, and then we'll dive in. So I'm going to be focused on quadratic number fields. So these are the simplest sort of non-trivial number fields, just degree 2 extensions of the rational numbers. They're formed by just adjoining a quadratic irrationality into that field. So these are completely parameterized by discriminants. So it's really easy to write one of these down. You just pick an appropriate integer delta and you've got one. Writing down the maximal order, the largest ring of algebraic integers inside that, is also in the quadratic case an easy process. So we got our maximal order quite easily. These come in 2 different flavors. So if the discriminant is negative, then you can immediately see that the quadratic field is a subset of the complex numbers. And so it's called in that case an imaginary or complex quadratic field. Whereas if delta is positive, then it is a subset of the real numbers, and it's called a real quadratic field or an order. These 2 different types have quite different properties arithmetically, and we'll see some of that as we go through the talk. Okay. So the 2 main objects one's usually interested in studying these things in a computational sense are the class group and the unit group. So if you take 2 integral ideals in the maximal order, we say that they're equivalent if they're equal up to multiplication by principal ideals. Those are ones that are O delta modules generated by a single element in the ring. That notion of equivalence does form an equivalence relation, and it partitions this infinite set of integral ideals into a finite number of equivalence classes. And there is a group operation on that, and that is the class group. It's a finite abelian group, and the class number, which we'll denote by h of delta, is just the size of this particular group. Now, of course, the main topic of my talk is all about the group operation there, so I'll talk about what that is and how that looks like as we go on. Now, the unit group turns out to be interesting in at least one type of quadratic fields as well. For the imaginary case, there's not much going on, so we say this as unit rank 0. So there's no non-trivial units other than roots of unity. So in particular, in the quadratic case, it means that there's only finitely many. In almost all cases, it's just plus or minus 1, but you can have as many as 6 if certain roots of unity are there. But in the real case, it's a little bit more exciting. We have a unit rank 1 case, so the units form a finitely generated group, rank 1. We say that the largest unit bigger than 1, we call that the fundamental unit. It's the generator of the cyclic, infinite cyclic part of the group. And the regulator is just defined to be the logarithm of that thing. So, quite different already behavior of the two types of quadratic fields. Now, why quadratic fields? So even though these are the simplest types of number fields beyond Q that you can look at, there's lots of stuff that we just don't know about them. Now, my motivation, and every talk in here is going to use class groups in a different way for and what makes it fascinating for all sorts of different purposes. Now, I'll focus on some of the more computational aspects of which that are most interesting to the stuff that I do. So one is that, again, there's lots of unproved conjectures about just basic properties of some of these invariants. And from a computational sense, we have no idea how to prove these things, but what we can do is try to do large-scale numerical investigations in order to generate evidence for their truth. So one famous one is the Gauss conjecture, which states that there are infinitely many real quadratic fields of class number 1. I don't think anyone would say that we're anywhere close to being able to prove that, but there's a good deal of numerical evidence, through extensive computations that that leads us to believe that this is true, and that these actually occur with a particular proportion or density. Yesterday, Renata talked about the Cohen-Leinster heuristics as well, about P ranks of class groups. There's lots of different Cohen-Leinster heuristics, all about the odd part of the class group. Genus theory tells us what the even order subgroups of the class group do pretty much completely, but the odd part seems to be very mysterious. The Cohen-Leinster gives us good predictions about things, like how often a particular odd prime divides the class number. Again, no proofs of these things in general for the quadratic case for sure, but lots of numerical evidence in support of them. Now, a second mathematical motivation. So again, is I had to put this in just in honor of Michell here, who of course has done a lot of work on Diophantine equations. So the Pell equation is one particular famous example of that. Just solving x squared minus dy squared equal to 1. And the best ways to solve that, or most efficient ones, involve computing the fundamental unit of an associated real quadratic field. You can compute that, then you can find the fundamental solutions of the Pell equation. Now, lots of Diophantine equations reduce to solving Pell equations in one way or another as well. So this is a fairly, being able to compute this efficiently is often a pretty important tool in the toolbox for Diophantine equation analysis. And even just the history of that equation itself is already of great interest, and lots of fun and interesting mathematics has been developed in an effort to figure out how to solve this efficiently. In fact, it's even possible to write over 500 pages in a book just on this one equation alone. So lots of really cool stuff that you can do with this. Again, and for many of those algorithms, it's really important that basic arithmetic in the class group be as fast as possible for those things to be efficient. Now, if you don't know, I live and work in a computer science department, so I got to wear two hats all the time. I had to, talk to math people about math motivation stuff, but in my day job, I have to talk to a lot of people about cryptography, because that's kind of another motivation for doing a lot of these things. And quadratic fields have had a sort of long and storied history in that realm as well, especially in the context of public key cryptography. So Buchmann and Williams invented this idea of using these objects for cryptographic purposes in 1988. Johannes Buchmann, incidentally, was my PhD supervisor. Hugh Williams, who I co-authored the book in the previous slide with, was my master's supervisor. So I come by my interest in these things quite honestly through these guys. But they made the observation that some of these computational problems are seriously hard. So computing discrete logarithms in the class group, we don't have efficient ways to do that. Computing generators of principal ideals given a Z-basis representation of the ideal also seems really difficult in a computational sense. And they described how you can leverage that presumed intractability of those problems for a secure key exchange protocols. And this was later generalized to digital signatures and probably a couple other things. Now, I only mention this though for historical context. These particular cryptosystems are really no longer of practical interest. So it's fun to read about them, but don't think to try to do further research on key exchange just using quadratic fields. In practice, elliptic curves are more secure. The discrete logarithm problem seems to be even harder. The group operation is faster, and people prefer that. I would bet that when I connected to Zoom here, there was probably elliptic curve key exchange and digital signatures going on under the hood to do it. It's very widely used. Another fact is that all of these problems can be solved efficiently by quantum computers. So if they ever build one that's sufficiently large, all these things would be insecure. And so people are no longer really interested in this aspect of it. However, in recent years, there's been a little bit of a renaissance, I guess, of quadratic field-based cryptography. So I just want to highlight some of these really neat applications as well as a positive motivation to look at cryptography using number fields again. So Castagnos and Laguilomi in 2015 devised a really neat construction, which is a hidden subgroup with an easy discrete logarithm problem. This uses relationships between class groups of maximal and non-maximal orders in imaginary quadratic fields. And they have a series of papers with some really interesting cryptosystems with new functionalities that we couldn't do well before, including a linear homomorphic encryption, which means that if you take some ciphertexts and form a linear combination of them, and you decrypt the result, you get a plain text, which is an analogous linear combination of the original plain texts. So really useful property. Encryption switching protocols, they have some other signature scheme and a whole bunch of stuff. Again, all of this using arithmetic and quadratic fields. More recently, Pietrzak and Wesolowski have both independently described something called a verifiable delay function using arithmetic and class groups of quadratic fields. This is another really interesting cryptographic construction that plays an important role in some blockchain design. So a lot of current interest. In fact, a few years ago, there was a competition by the Chia blockchain consortium about the most efficient way to do squaring in the ideal class group. But they had a $50,000 reward attached to it for the fastest implementation of that. Unfortunately, I didn't know about that until the competition was already over, but it just goes to show how much sort of the corporate interest there is in these sort of things now. The security of those, incidentally, relies on the fact that computing the class number is believed to be a hard problem. And there's actually a bunch of other interesting cryptographic protocols based on the same hardness assumption of basically the order of the class group not being known or computable, efficiently computable. Integer commitment protocols, accumulators, there's other interesting types of signature schemes. And there's a whole little industry of applications of that, in which, again, class groups of quadratic fields are one of the best settings available to realize these in practice. Now, finally, you might complain that those first two applications aren't quantum resistant either, because if we have quantum computers, we can compute the class numbers and break all these things anyway. But the last one, though, some cryptosystems using isogenies of elliptic curves also make use of class group class group algorithms. In particular, something called Sci-Fish, which is an improved seaside protocol that uses the knowledge of a particular class group in order to speed up encryption or a key exchange, I forget which. And in fact, this was the motivation for the current record for computing the class group of a quadratic field, a 154-digit discriminant. It was done in order to provide faster arithmetic for that particular cryptosystem. So, and that one is quantum resistant. So lots of things going on with this. And again, motivation for my talk, given all that motivation, is that for all of those applications I was talking about, it's really crucial that the basic group operation in the class group be as fast as possible. The cryptosystems, have them fast depend on that. In fact, the verifiable delay functions, if you can find a faster way to square ideals in the class group, you could potentially sort of win in some of the blockchain competitions that in the Chia blockchain, and perhaps make some money or something. So it's important that they want to know, the fastest way to do this so they can set their security parameters accordingly and prevent that. Doing numerical investigations for unproven conjectures. Again, a lot of the algorithms we use, rely heavily on class group arithmetic. So the faster we can make that go, the faster and more extensive tabulations we could do for those problems as well. So I'm going to show you now the rest of the talk, what the state of the art is for that basic, and hopefully you now agree with me, important operation. And then at the end, with whatever time I have left, I'll talk about the analogous results for the case of hyperelliptic curves, which are the function field analogs of quadratic fields. Okay. So the basic operation in the class group then is multiplication of integral ideals, and reduction, I should say. So when you have equivalence classes, how do you do group arithmetic with them? Well, you try to identify a representative of each equivalence class, do the group operation on those, and that gives you a representation of the product of the two classes. And it's the same thing here. Our equivalence classes are made up of an infinite set of integral ideals. We want to find representatives of each, and we can multiply those together. So the first question then is, well, what does an ideal look like in a quadratic field? Well, you can describe these a couple of different ways. I think, to my mind at least, the most useful one for computations is like what I have written on the slide here. So they're two-dimensional. You can write them as two-dimensional Z modules and describe them basically with a triple of integers. So remember, the discriminant describes the field, and then for a particular ideal inside the maximal order of that field, we just need integers S, A, and B, and that gives us the Z basis for that particular ideal. These integers have to obey certain properties. So A is unique, B is uniquely defined modulo 2A, and we always have this divisibility property that 4A divides exactly a B squared minus delta. Two terms that I'll need the next slide or two. The norm of an integral ideal is just the index of the ideal in the maximal order. In this representation, the nice aspect of it is we can immediately write down what that norm is. It's just S squared times A. And the conjugate of A is just, again, the ideal that consists of all the conjugates of the elements inside of it. In this representation, it's easy to write down as that as well. We just negate the B coefficient. Now, what about multiplication? Well, if I have two ideals here, given as two-dimensional Z bases, to form their product, I just find the four-dimensional Z basis that consists of the products of each of the generators, all four possible products. That's the basic idea, and from there you can actually derive an algorithm fairly easily to do this and recover the representation of that of the product ideal in the form that I put above here. In fact, the formulas to do that are actually due to Gauss. This is really nothing more than Gauss's composition law on binary quadratic forms. In fact, binary quadratic forms give you essentially an isomorphic way to represent the class group of at least an imaginary quadratic field. And you can also use them to represent real quadratic fields. So this is no accident that it's Gaussian composition that does the job for us. Now, what about arithmetic in the class group then? So again, the idea is we find the representatives, try to designate representatives of every class, take ideal representatives and use Gaussian composition to multiply them, and that gives us a representative of the product class. So in the class group then, the identity element is just the class of all principal ideals, and it's the simplest principal ideal we can take to represent those is just the order O delta itself. If you want to do group arithmetic, you also would like to know how to invert elements in your group. Inversion in the class group is pretty easy. To invert a particular class, we just take a particular representative of the equivalence class and take its conjugate. And I claim that that represents the inverse class in the class group. That's fairly straightforward to see because we know that if you multiply an ideal by its conjugate, you get a principal ideal generated by the norm of the ideal. And so in particular, that means that if you multiply the class represented by A and the class represented by A conjugate, you get the principal class. And so those are indeed inverses of each other in the class group. So that's pretty easy to do as well. How do we pick representatives? So there's infinitely many ideals in each equivalence class, but you want to kind of here do the same thing that you would do for integer arithmetic modulo prime. When you do that, you usually are just going to pick the smallest remainder modulo the prime as the canonical representative of that entire equivalence class, because those are the smallest. They're going to be the easiest to do arithmetic with. And in this case, we want to do the same thing. We want to find ideals in each equivalence class that are small in some sense and use those as our representatives. And so there's this notion of reduction then of ideals. So we say that an ideal is reduced. If first of all, this coefficient s is equal to 1. That means that the ideal is primitive. It has no integer sort of factor in it. And then, also subject to this other condition that, there's no non-zero element that's such that the element and its conjugate in absolute value are both less than the norm of the ideal. That property, what that is saying is that the norm of alpha is a minimum in the lattice A. All these ideals are, two-dimensional lattices. But the main consequence of this is that every reduced ideal has small coefficients, in particular A and B are both bounded by the square root of delta. Okay? And so that's pretty good. Now, if you run with that, it gets even better. So if you look at the imaginary case, if you're careful and precise about how you define reduction, there's a little bit of ambiguity that can arise from this basic notion. But if you deal with that, then you can say that every ideal class has a unique reduced representative, which is great for computation. That means to do arithmetic in the class group, I find my representatives of the two classes, the unique reduced ideals, I multiply those together, and then I find the unique reduced ideal equivalent to that one, and that gives me a canonical representation of the product of the two inputs. This is also good if I need to test equality of the elements in the class group, which need not be easy. These are equivalence classes. And here, the fact that there's unique canonical reduced representatives means that I can do equality testing just by comparing these representatives. Very easy. The real case, either unfortunately or interestingly, depending on your perspective, is much harder. In particular, under the same notion of reduction, the best that you can show is that every equivalence class has finitely many reduced representatives. As a side note, that fact is sort of the basis for proofs of the finiteness of the class number, in fact. But it's the best you can prove is finitely many. And in fact, in the real quadratic case, you have that there are roughly R delta, or the log of the fundamental unit, reduced representatives. And so this makes arithmetic in the class group considerably harder, for the basic fact that it's now a problem to decide whether two equivalence classes are equal. we can find a reduced representative of each class, but it's no longer unique or canonical. So you have to work a little bit harder. You have to find all of, in some sense, all of the equivalent reduced ideals in a class in order to figure out whether that class is equal to another one. So in particular, this implies is that class group arithmetic now has to work with what are called relative generators to help distinguish. So you take one reduced representative, find all the equivalent ones, and you have to know which principal ideal you multiply your original one by to get all the other ones. You have to keep track of those things explicitly as well. So not quite as easy, but still, at least multiplication and reduction is the best that we can do. All right, so the main thing then is multiplication of integral ideals. So what I've put up on the slide here is essentially a Gaussian composition. There are a variety of ways to formulate that. This is, in my experience, probably the most efficient one, the most amenable one for computations. And so you see here how this works. If you haven't seen composition before, this is what it looks like. And this can be derived, again, very easily from what I had in a couple slides ago of just taking the four-dimensional Z module and just doing some elementary arithmetic to do these computations to get your two-dimensional Z basis. The main work here is computing this extended Euclidean algorithm here. So we have to find the GCD, greatest common divisor of A1, A2, and B1 plus B2 over 2, and the corresponding Bezier coefficients. And once you've done that, there's some fairly elementary computations here, and you get your answer. Okay, so fairly simple operation. Right. And if I had to bet money, I mean, if you know how to multiply ideals in quadratic fields, this is most likely the algorithm that you know, or some basic variant of this. But the interesting thing is that we can do considerably better than this in practice. Now, to see how that can be, so I want to point out the following observation here. So again, our assumption is that the input ideals A1 and A2 are reduced ideal representatives of class group elements, so these equivalence classes, meaning that the coefficients in the Z bases that describe them are all bounded by the square root of delta. Okay. So in particular, the quantities A1 and A2 in each one are less than square root of delta. But look what happens when I multiply the ideals together. In the last step in particular, the A coefficient for the product ideal is formed by multiplying the A coefficients of the inputs, and then dividing out this greatest common divisor here squared. Right? Now, if you think of these integers A1 and A2 as just being random, then you know that with fairly high probability, this GCD-S is going to be very small. In most cases, it's equal to 1, in fact. So what that tells you then is that when you do this multiplication, you form this product, that the coefficients of the product ideal A and B are now no longer bounded by square root of delta. They're now of size delta. So in particular, it's no longer reduced. Okay? And so after that, you have to do a reduction, which basically is applying the continued fraction algorithm to B plus root delta over 2A in order to reduce it. I'm playing a little bit loose here because when delta is negative, of course, it's not exactly this. This is really in the real case. When delta is negative, you do something more or less analogous to this. Gauss's reduction algorithm can kind of be viewed in similar sort of fashion to this. But that's basically what you do. You do continued fraction algorithm on this and this quadratic irrationality, and it reduces B and A. And furthermore, the quadratic irrationalities that you get through that process also define equivalent ideals, and eventually you get one that's reduced. Okay. So that's sort of annoying though, right? So you start with ideals that have nice small bounded coefficients, and as soon as you multiply them, they get bigger and you got to reduce them again. We'd like to keep things small, for efficiency. The larger integers get, the more expensive it is to do arithmetic with them. So we'd like to kind of not have to do that if we could possibly manage it. And so this is where Daniel Shanks came in back in 1988, who devised an algorithm called NUCOMP that I think deserves to be more widely known than it is. Computer algebra systems like Paris and there's Sage is built on Paris. I think Magma all implement this. But I'm not sure, how much more widespread it is beyond that, or they implement a version of it at least. Now, Shanks's motivation, so his paper, this is actually the last paper he wrote, and it's called On Gaussian Composition 1 and 2. And the paper is a really fun read. It's a really sort of written in a very sort of tongue-in-cheek manner. There's motivational content, related to movies that Dan Shanks liked. There's one called Ninochka from the 1930s. And he describes the operation of NUCOMP with allusions to that movie. It's really fun to look at. And he describes his motivation being that he wanted to be able to do a composition of binary quadratic forms or class group arithmetic on his old Hewlett-Packard programmable calculator, which had a limit of 9 decimal digits for its operands. So the fact that, whenever you multiply ideals, that you get a coefficient before reduction that's the square of the inputs, was a pain for him, because that meant that he could only work with the 4-digit ideals, and he wanted to expand that and be able to do coefficients with bigger things. So he came up with this idea of doing some sort of a partial reduction before completing the ideal multiplication. And the result of that, you get a more complicated algorithm, but you do this reduction of the intermediate operands and then combine them. And that just keeps the sizes of everything lower, so that you never blow up to size delta, you stay much smaller, and he could now use his programmable calculator to do more computations. Okay. Now, so Shanks and the genealogy here, so Shanks had that idea, and Oliver Atkin looked at this, and in some unpublished letters to Shanks described some important improvements to make it work even better in practice. And these were described in the language of binary quadratic forms and unimodular matrices. Shanks's paper refers to something called the magic matrix, where all this reduction happens. And Alf van der Poorten, picked this up and described how to adapt what Shanks and Atkin had done for real quadratic fields, in particular describing how these important relative generators can get computed along the way with it. But Renat and Hugh Williams and I looked at this again and figured out how to have maybe a simplified version of how this works involving continued fractions. And the main observation that describes how this works is that, again, reduction of ideals, the traditional way, you compute the product with coefficients a and b, and you have to reduce this quadratic irrationality b plus root delta over 2a. Well, the observation is that you can get a really good rational approximation of this with intermediate values in the multiplication algorithm. So that quantity capital U, the GCDS, and one of the, that should be A2, sorry. One of the coefficients of the input ideals, this rational number here is really close approximation to this one. And in fact, the continued fraction partial quotients agree for quite a while. So what that means is you can figure out what the continued fraction of this quadratic irrationality looks like, at least for several steps, without actually having to compute B and A themselves. You can just use a U, S, and the A double prime or A2 here, and you can figure out the continued fraction. And then Shanks's brilliance in this was to figure out, well, if I know what those steps are, he came up with formulas to then figure out what the reduced ideal AB looks like just by knowing those partial quotients and these intermediate values. And so that's how you do it. So you don't do the full multiplication and get the big coefficients. You use partial reduction first and use these fancy formulas to get your answer, and you can avoid most reduction. And the one other, I guess, extension here that I'll mention is that Laurent Imbert, myself, and a former postdoc, Arthur Schmidt, also looked at this. We described how to do cubing of ideals. So Shanks could do multiplication and squaring. And we tweaked the formulation a little bit and made it a little bit slicker and faster. And that's kind of the state of the art where that's at. So here's the algorithm, just to show you, sort of how and why this works a little bit. Again, this starts the same as before. So we compute the capital U and the GCDS just as before. And then the next steps here are basically working out the simple continued fraction expansion of the rational number capital U times S over A2. That's what this is. Steps 2 and 3 are just that basically the Euclidean algorithm working out that simple continued fraction. And again, the observation is that the Q values here, the partial quotients here of this simple continued fraction exactly match up to a point the partial quotients you would get if you had actually done the multiplication and did them on the quadratic irrationality b plus root delta over 2a. So we compute them in this way instead, and then step 4 is the magic formulas that give you your answer. So you just compute M1 and M2. I should mention these divisions here are exact by capital L, and then the output to values A and B are going to be almost reduced. And you might have to do a little bit of reduction after, but I think we proved that you have to do at most 2 reduction steps and you finish. Now, why does this help? Well, the key is in this sort of termination condition here. So we do these continued fraction, simple continued fraction steps up until this quantity, this remainder Ri is less than or equal to essentially the 4th root of delta. Now notice if you do that, what's happening is the sequence R, these are these decreasing remainders. And the sequence C is, these are increasing as we go. And if we stop here, then Ri and Ci are both approximately the same size. And if you go through here and look at the sizes of the operands that you get in M1 and M2 in computing A, well, you see that, for example, Ri is of size delta to the 1/4. N is basically A2, so that's of size delta to the 1/2, assuming the input was reduced. And when you divide by L, which is also of size delta to the 1/2, we see that M1 is of size delta to the 1/4. You can do the same analysis on M2. It's also roughly of size delta to the 1/4. And so when you compute A here, Ri times M1, you're multiplying 2 things of size delta to the 1/4. And same with Ci times M2. And you get that A is about the size square root of delta, which is exactly where you want it to be for your answer to be reduced. Okay. And so the upshot of this is that instead of having to work with integers of size as large as delta, you get them down to about delta to the 3/4, which made Shanks happy because he could use his calculator to do bigger class groups for larger discriminants as he wanted. Okay. Now, just to show you a little bit that this actually works, so here are some times that are taken from my paper with Schmidt and Imbert, just comparing the time to do basic Gaussian composition reduction as compared with NUCOMP for increasing discriminant sizes. And the timings here are just, we're doing just some binary exponentiation here of ideals, just as a means to measure these things. You can see that as the discriminant is getting larger, the disparity gets quite big. And NUCOMP becomes better and better as discriminants get larger relatively to just multiplication and reduction. So in practice, this can make a huge difference, especially if you're doing computations like cryptographic sized fields. It's a very important optimization for what you want to do in practice. Well, the most recent results we have of this are done with a former master's student of mine, Maxwell Sales, in 2016. He looked at some empirical evaluation of the really crucial extended GCD steps, looking at things like a binary GCD algorithm, Lamer's variant, if you've heard of those, really important practical optimizations to find out the best ones. I didn't include any of his results because his focus was on sort of smaller bounded operand sizes, but still, his results are also applicable to these large sizes as well. And that, I think, is the state of the art for number fields. Okay. So if you hadn't heard of NUCOMP before, hopefully I've convinced you that it's a really useful tool for doing ideal arithmetic. And for pretty much any serious computations where you're looking at reasonably sized discriminants, it's definitely the algorithm of choice for solving this problem. All right. So in the last couple of minutes, I want to talk briefly about the analogous situation in function fields, which are hyperelliptic curves. Okay. So what I'm looking at now is the so-called degree zero divisor class group of a curve, algebraic curve of the form y squared equals f of x. I'm looking at this now over a finite fields. For simplicity, I'll assume that my finite fields all have odd characteristic. That's not necessary. Everything I'm talking about works equally well in any quadratic field, and actually any field itself in general. I think it's just a little bit simpler in this case. So this curve is a hyperelliptic curve of genus G here. The genus is related to in the context here the degree of f. So if the degree of f is equal to 2, if it's odd, then the genus is degree of f minus 1 divided by 2. And if it's even, it's degree of f minus 2 divided by 2. It gives you the genus. Elliptic curves, incidentally, are hyperelliptic curves of genus 1. So that may be a more familiar object, perhaps. But that's what these things are. These come in 2 flavors as well. So we call these ramified, or you can look at ramified or split models of these curves. Again, if the degree of f is odd, we call this an imaginary or ramified model. If it's even, we call it a split or a real model. Terminology is not accidental either. So ramified or split refers to what happens to the infinite place in the function field here. And they're also sometimes called imaginary or real because the function fields of these curves have really strong analogs to imaginary and respectively real quadratic number fields. Okay. So in particular, it's the degree zero divisor class group is the main invariant of interest. In the imaginary case, that group is isomorphic to the ideal class group of the function field of the curve. So that's basically, you're taking the field of rational functions, so quotients of polynomials with coefficients in FQ, and you adjoin to that the quadratic irrationality y. So remember, my curve equation is y squared equals f of x, so y is in some sense the square root of x in some appropriate completion of this field of rational functions. So, and in the imaginary case, that function field, the ideal class group, is isomorphic to this degree zero divisor class group. And in the real case, this function field has a has a fundamental unit, just like real quadratic fields. It's a unit rank 1 unit group. And in that case, the relationship between the function field and the ideal class group and the degree zero divisor class group is that the order of this divisor class group is equal to the class number times the regulator, where the regulator is defined as the degree of the fundamental unit. So very close parallels and analogs with these objects to number fields, especially when you go to the function field model. So what about the group operation here? Well, in a hyperelliptic curve parlance, we speak of the Mumford representation of a divisor. Well, that's just given by a pair of polynomials, u and v, with coefficients in the finite field fq that satisfy these properties. So we demand that u be monic. V is defined mod u. We have a divisibility condition that u divides v squared minus f. And we say that our Mumford representation is reduced if the degree of v is less than the degree of u, and that's less than or equal to the degree of g. Now, in fact, this Mumford representation, if you can look at a degree 2 fqx basis or dimension 2 basis of a corresponding ideal in the function field, and you get something that looks very, very, very much like the ideals that I described earlier. And so it's very close analogs here. And similarly, in the ramified or imaginary model, these reduced divisors and Mumford representation uniquely give canonical representations of elements of the class group. And in the split case, one difference between the number field case is that we can get unique reduced representatives if we go to something called balanced representations. So, but still, very close and analogous situation. What about the group operation? Well, in the hyperelliptic case, we speak of what's called Cantor's algorithm. which I put on the slide here. And I don't expect you to, of course, have remembered this algorithm if you haven't seen it before, but if you get a chance to look at this stuff again, the algorithm that I'm presenting here, it was a formulation of Cantor's algorithm, and this looks almost identical to the version of Gaussian composition that I had earlier in the talk. Okay? The main difference here is that the quantities that we're operating on, U1, V1, U2, and V2 are, instead of integers, they're polynomials with coefficients in finite fields, but still we do this extended GCD algorithm step. We compute this quantity capital U, and then we form the sum of the divisors here by multiplying the two U coefficients and dividing out the GCD squared. It's almost identical, right? This is one reason why people who do, arithmetic and computational work in class groups often go over to the algebraic geometry side, because you can do so much of what you know in one setting transfers in an algorithmic sense to the other one, and there's a lot of fun things you can do. And now, one other thing about this, so last time I motivated NUCOMP for the number field case. So here we have a similar thing happening. So if D1 and D2 are reduced divisors, then the degrees of U1 and U2 are both bounded by G. But when we add them together using Cantor's algorithm, the result is I have a non-reduced divisor, because my U coefficient is now going to have degree twice G. Right? So I got to do the same thing again as in the number field case. I do this algorithm to add my divisors, and then I have to do some type of a reduction, which also turns out to be related to a continued fraction expansion of a quadratic irrationality. Remember that y comes from my hyperelliptic curve equation, and it's basically the square root of f. So very similar. And again, here now, y, again, and here you can actually use sort of language of continued fractions to essentially unify the ramified imaginary or split real models. But the reduction basically amounts to doing a continued fraction of that. And so NUCOMP is also applicable. So Alf van der Korten and I looked at that in 2002. We made these observations that, hey, Cantor's algorithm and Gaussian composition are doing essentially the same thing. I bet NUCOMP works here too. And sure enough, it does. Again, using the same kind of ideas for number fields, that this quantity U times S over U double prime is a pretty good rational approximation of this quadratic irrationality V plus Y over U. Okay. Renata and I and Andreas Stein did a similar thing as what Hugh and Renata and I did in the function field case here. We, put the formulation and exposition of this in the framework of continued fractions instead of magic matrices. Clean it up a little bit, improve the efficiency of the operations. In the same work with Imbert and Schmidt, we looked at the analog of cubing, which of course tripling in this additive context, slight optimizations to the formulations. And the most recent work in this was Laurent Imbert and my PhD student, Sebastian Lindner. We described how you can apply NUCOMP to split model curves using these balanced divisor representatives. I mean, we certainly knew how to do NUCOMP in real models before, but this special formulation that gives you unique representatives in the real case, no one had worked out the details. So we did that, did the legwork for that. And the upshot is that now NUCOMP is the method of choice for hyperelliptic curves of genus bigger than or equal to 5. It's faster, and as the genus gets bigger, NUCOMP gets increasingly more relatively efficient than Cantor's algorithm, just like with Gaussian composition and NUCOMP in the number field case. Okay, so again, NUCOMP, and if you don't know about this, if you're interested in function fields, this is also a really important algorithm to be aware of. I don't believe this is yet implemented in any of the computer algebra systems, but I have an undergrad student who's just started working on that, and hopefully that'll come soon. So the last thing I want to briefly mention is one interesting thing that you can do in function fields or hyperelliptic curves that you cannot do in number fields. This is the idea of explicit formulas. Okay? So you might ask, I said that NUCOMP is the method of choice for genus bigger than or equal to 5. You might ask, well, what about genus 1, 2, 3, and 4? Well, genus 1 is elliptic curves, and you've probably seen how to do the point addition, chord and tangent method for the group law, and that's of course what you do there. Hyperelliptic curves of genus 2 and 3, we do something a little bit different. So instead of describing our arithmetic operation in terms of polynomial operations like NUCOMP and Cantor's algorithm do, what we do in practice is we kind of blow that up, and we describe everything in terms of operations on the coefficients of the polynomials themselves. So we just deconstruct everything. Every time we multiply or do an operation in polynomials, we just write down the sequence of operations on field coefficients. Now, the reason you want to do that is because this gives you further opportunities to optimize and streamline the formulas. So you can do things like eliminating redundant computations or minimizing field inversions, which is especially important because to compute an inverse of an element in a finite field, integer arithmetic mod p, you've got to do the extended Euclidean algorithm, which is much slower than just multiplying and dividing. So you really want to do that. And by breaking things down in that painstaking way, you can get things much faster than just doing things generically. So lots of other tricks that are used. One important one I'll mention is Montgomery's trick. So again, you really want to have as few field inversions as possible. Notice every time you divide by a polynomial or try to compute a remainder, you have to invert a field element. So what we do is we basically arrange things so we figure out all the things we want to invert, we multiply them together and just do the inversion of their product. And then you can recover the inversions of any individual element with some extra multiplication. So this is called Montgomery's trick. It's named after Peter Montgomery, who is a brilliant mathematician, worked at Microsoft Research for many years. He unfortunately passed away in 2020, but he's got one of the main some of the main efficient things for elliptic curve factoring method as well. So that's what we do in practice. Sebastian and I, another undergrad, Randall Apperly, have been doing work on this. So we use our formulation of NUCOMP and just expand all that in order to come up with these explicit formulas. These tables list the number of field operations, multiplications, and additions. You see, genus 2, we get slightly better in most cases. Genus quite a bit. Yeah.
Just to caution you on time part.
Yeah, I'm pretty much finished. Yeah, that's it. So this really works. You can these explicit formulas do quite a bit better. Using NUCOMP, you get better than the state of the art. For split models, the same thing. We've been doing some work on that. The same people getting some improvements, and publications of that are in progress right now. And so to finish up, what else are we doing? Well, after quadratic, the next simplest cases are cubic and quartic fields. Ha Tran and PhD student Randy Yee are working on the cubic case. David Marquis and I are looking at the quartic fields as part of some bigger projects we're working on. Cubic fields has the advantage that you can do at least special purpose reduction algorithms via Voronoi algorithm. Big open question is whether NUCOMP can work in any of those settings. I know Alf and Renata tried that in the cubic case and seems to be pretty hard. It'd be cool if it worked. For curves, we're also looking at similar questions for non-hyperelliptic curves. And finally, one cool thing that we can do in the curve case, explicit formulas are really hard to generate. But undergraduate Haiyang Yi and I, just this last summer, figured out that you can automate the process completely. And all this painstaking labor that people used to do by hands, and it's a lot, we can do this all in computer now. And there's ongoing work to optimize that approach. And we hope that we're going to get better arithmetic for 4 and 5. So we'll have the complete range of genera covered from 2 up to infinity. So I'll end with that. Sorry for being a couple minutes over. Just thank you for your attention. And again, hopefully next year we'll be able to make it out to some of the beaches that Colin was talking about before my talk. Thank you very much.
Thank you, Mike. So let's thank the speaker. I can't hear any claps, at least from seminar hall. People should. I request everybody to thank the speaker.
The mic was turned off.
Okay. And maybe we can take a few questions. So is there any question from seminar hall? Doesn't seem any. So is there any question from online audience? Okay, doesn't look like. So, okay, thank you, Mike. Actually, say these computational things we also need quite a lot when we try to do some research, like some idea to see whether things will go ahead or not. We need, and one question I have from my side. Mike, can you hear me?
Yep.
Yeah. One question I have, like what you talked about multiplication of ideals. But given two ideals in a number field, how to distinguish whether they represent same ideal class or different ideal class? Is there some, I mean, what is the quickest way to distinguish that?
Yeah, so that relies, in the quadratic case at least, this notion of what's called infrastructure, right? Which that would have been a fun thing to talk about as well. I could have probably filled the whole lecture with just that. Basically, the idea there is that you can do some computational tricks in any particular equivalence class, and so you can answer questions like whether or not two ideals are equivalent using some pretty heavy ideal arithmetic-based computations. And baby step, giant step is probably the one way to do it. You can use index calculus for it as well. But in short, it's a hard computational problem in general. But there are some improvements to do it. Infrastructure is what you want to look at for